Okay, let's come back to class. So basically, in the last lecture, we have been introducing the definition of the network flow problem and basically the maximum cut, the minimum cut, max flow problem. Those kind of problems, and I guess we are gradually moving into such kind of basically want to observe the structure of the problems. Basically, we first have this flow value lemma here. That actually the value of a flow here, we can actually in general taking this, I mean, for an arbitrary cut here, we can compute this function f e for all the e out of a minus with the summation of f e e into a here. That actually in general, I mean, for an arbitrary cut, a b cut for st cut, I mean, with a set a here, we can actually compute the corresponding value here. And I guess the next thing that we are basically going to show is the weak duality here. And in general, I mean, as long as we have actually a flow here, we have an st cut here. Then the value of the flow is at most the capacity of the cut. I mean, for instance, if you are clever enough, then maybe you actually figure out a cut. Actually, the capacity is actually decently small. This just, for instance, in this example, actually the capacity of this cut is actually 29 here. This just means that due to the weak duality result, we can imply that the flow value is actually smaller than 29 here. So let's actually then prove the weak duality here. So the proof is actually quite straightforward. It's just like recall what we actually proved above for the flow value lemma here. So according to the flow value lemma here, we know that the value basically this Vf actually it equals to the summation of E out of A. Fe minus the summation of E into A, Fe here. So without loss of generality, I mean, in general, we know that we are minus a value here, and actually Fe is actually larger than or equals to 0. So we know that the summation is actually, this value is actually just smaller than the summation of E out of A, Fe here. We just ignore the second term, and this becomes to an inequality. But furthermore, we know that basically due to the definition of a flow here, we have this capacity constraint that actually Fe is actually smaller than Ce. So actually we know that this is smaller than or equal to the summation E out of A, Ce here. And actually it is not hard to say that this just equals to the definition of the capacity between A and B here. And this basically is the proof of the weak duality result. And actually, following this weak duality, basically this let's call it the weak duality lemma here. So a very direct corollary that we can see is that basically so we let F be any flow, and actually AB be any cut. So if we can find a flow at a corresponding AB cut, such kind of following that Vf equals to the capacity of AB here, then we are pretty sure that F is a max flow. And actually, on the other hand, AB is a mean cut. So this is a direct corollary of the weak duality lemma, because in the weak duality lemma, we have proven that actually the value of the flow is actually at most the capacity of the cut. I mean, here basically the value is arbitrary and the cut is also arbitrary. I mean, if there is actually a case that for a certain flow and a certain cut here, the value of the flow can reach the capacity of the corresponding cut. I mean, then it is just straightforward that this F is the F you choose must be a max flow here. Otherwise, I mean, if it is not a max flow, there is even a flow whose value is actually larger than this Vf and larger than this capacity of A and B here. It's just like you're going to get a contradiction with the weak duality lemma. And also vice versa, you can also clearly see that AB here it must be a mean cut. Okay, so any question about this proof of the weak duality lemma and also the corresponding corollary? I guess here it's just like it's a very direct use of this this flow value lemma that we are actually having here, and basically having this observation is directly related to the capacity of the cut A and B. Okay, so any questions? So basically, I mean, Very first, I mean, based on this corollary, I guess maybe for instance, let's take a look at this. I mean, here, I mean, basically for this graph. So we have it here, and also on the other hand, I mean, we have this cut here. So we also have this cut here. I probably can't. Let me just paste it here. So here, I mean, what is the direct impact of this corollary here? So here, I mean, for this instance, actually, I'm giving you both a flow actually with value of 28 here. And also on the other hand, I'm actually giving you a cut with a corresponding capacity 28 here. I mean, directly looking into this corollary, I mean, having a both construction, I mean, a flow here, and that's actually also a cut here with their corresponding value and the corresponding capacity equal. I mean, you don't need to further check, I mean, whether your flow is actually a max flow or your cut is actually a mean cut. Actually, the flow must be a max flow and the cut must be a mean cut. I mean, conclusion here we have, we must have got the mean cut on the max flow. As they have equal value. Okay, so any question about this corollary and this observation that, I mean, as long as we can find a flow and actually a cut that their value is equal, we actually simultaneously solve the max cut and the mean flow. The mean flow. The mean cut and the max flow. So any question about this? Okay. So I guess basically, I mean, having this observation, I guess this is a very direct relationship between the max flow problem and the mean cut problem. I guess in general, I mean, this just suggests us that maybe it suffices that we solve one of them and maybe then the other problem actually the corresponding answer is then going to be straightforward. So basically in this lecture, I guess we are going to focus on the problem where we are going to find the max flow. So here we say we want to ask that in general how we can actually find the max flow here. So I guess in general, I mean, the main reason that we want to study the max flow problem is that it seems that this is probably a little bit easier to manipulate because in general, I mean, you want to consider like a subset of vertices. I mean, if you have like n vertices, I mean, in general, the cardinality of V here equals to n. I mean, if you have n vertices, the choices of the subsets, I mean, in general, roughly speaking, is O of 2 to the n. This is just too large. But nevertheless, I mean, we have a graph here, and basically want to utilize the structure of the graph, and basically consider like a flow there. Here is probably a little bit more intuitive. And I guess, I mean, in general, we want to think about how to find like a max flow here. I mean, a very straightforward way is maybe we want to, I think, a little bit more on this, and actually a direct idea that maybe we can think about is that maybe, for instance, we can do gradient. So about a greedy algorithm on this. So maybe you can think about, I mean, for instance, if you want to do this, I mean, for instance, using a greedy strategy, what is the strategy that you probably are going to use here? So it's still about, I mean, the most important question about like a greedy strategy. I mean, the most important question, as I'm always asking, is greedy with respect to what? So here we need to think about actually what is the point that we want to make this to be a greedy strategy. But in general, I mean, we are talking, I mean, you can probably think about, I mean, like a strategy that we are going to use here. So actually, for instance, in this example, so here we are actually basically drawing some paths here. So actually at the first, we only consider like a very simple case that we only have the red edges. I mean, the red edges here is actually going to give you a value of 4 here. But I guess you can very easily see that actually this does not fully utilize the structure of the graph. That actually, later on we find there's a blue path. That actually the blue path is going to give you additional value of 3. So basically from this example, this directly suggests some kind of a greedy strategy here is that maybe we want to always try some ST paths here. As long as maybe there is like a path that connects S and T here, maybe we want to push forward along this and actually increase the corresponding value and actually do this again and again until there is no ST paths. So this is actually a very direct thing that is actually going to suggest by the algorithm. And actually, let's write this in a more formal way. So we say that this is like a greedy algorithm that we can actually study here. And actually, of course, at the very beginning, we need to start. So basically, we need to start with Fe equals to 0 for all edge E in E here. So this is basically the first step. And the second step is that we need to find an ST path T where each edge actually has Fe smaller than C. If some of the edges already reaches the maximum capacity, you cannot like further improve this. So basically, we as long as we want to find an ST path, here we basically in general we only need to consider path where each edge along this actually satisfies Fe is smaller than Ce here. So actually in this graph, for instance, maybe when you want to consider this, maybe you can, for instance, just do this in a BFS or DFS if you prefer. So here, for instance, assume that you are currently in this graph here. For instance, like this edge already reaches the maximum capacity. You can just delete this edge. Actually, when you run this algorithm, you just delete the edge where corresponding weight has reached the maximum capacity. You just delete this. Maybe, for instance, then you run the BFS. And then to find like a ST path along this. If your BFS, in S, even does not find a T here, this just means that actually we are at the stages of the ending. Basically, for doing this, actually, in general, as was mentioned here, as long as you can find a ST path, you just augment the flow along F P. Basically, by augment, it's just until some edge reaches Fe equals to C. And basically, you do this again and again. You just repeat until you get stuck. Basically, there's no ST path where you change. So I guess this is a relatively straightforward strategy that in general, maybe we want to consider here a greedy algorithm. So basically, we in general, as long as we can have like a path, we can actually, for following this path, where the weight actually for all the edges, the weight corresponding F is actually strictly smaller than Ce. We just increase the corresponding value. We just do this again and again until there is no ST. So this is the first algorithm that we actually want to study here. So it's actually there a question about the statement. So actually, it is very natural, at least from my perspective, to propose this algorithm. But of course, the next question we are going to ask is this optimal? So maybe we can actually think a little bit about this, and maybe, for instance, is this optimal? From your perspective, if it's not, what is like a hard instance for that maybe this greedy strategy is not actually working the best? So I guess since I'm asking this question, probably the answer is no here.
You want to rewind. Maybe if someone has decreased the flow, you can trace the flow for some.
Yes, yes. So that is actually a main reason. I guess that is a good intuition here. So let's actually see an example here. I guess the answer is actually a no here. So let's see an example actually of only a few vertices here. So of course we are going to have an S and actually a T here. So in the middle, let's just assume that we have two vertices. So let's for instance consider a graph like this. So here, let's assume that this weight is 20 on 10 or 20 on 10, 30. So if we do this a greedy, I mean, if we do this in a greedy sense, and if the greedy, I mean the ST path, we choose, for instance, S21, 1 to 2, 2 to T here. So basically we choose this path. I mean, basically for this path, I mean, the corresponding capacity on these paths is 20, 30, 20 along this. So basically, I mean, by this kind of discussion, I mean, we can clearly see that we can actually put a value of 20 here. I mean, for this value. So basically, we have 20 here. Oh, I think I want to use the red color. So to the value of 20 here, and we put a value of 20 here, I put a value of 20 here. So after we do that, and we actually take another look of this graph here. So we notice that, I mean, after we do this, actually this graph does not have any ST paths anymore, because actually, I mean, after having this 20, this is not an available edge, and this is not an available edge. I mean, actually, but from S, I mean, consider all edges, we can only go from S to 2 here, but you cannot go from 2 to 1. So basically, this just breaks. And basically, this just suggests that currently we are not having any ST paths here. Actually, this concludes that basically for this graph, the flow value just equals to 20. So this is basically like a flow that we found out through the greedy strategy. And actually, this is a very important observation. So basically, the observation here we can like roughly speaking can be highlighted that as like note that a local optimality. I mean, basically this greedy strategy suggests some local optimality. That basically using this kind of current strategy, you already reaches your best, which is, I mean, in some sense, I mean, if you consider like overall many different strategies, I mean, at least you are optimal locally. But actually, unfortunately, for this greedy strategy, it does not improve, actually does not imply the global optimality. I mean, basically for this example, actually you can, you are able to construct a flow with value that is larger than 20 here. So for instance, let's consider this flow here. So here, let's assume that maybe, I mean, if it's larger than 20 here, so basically we need to utilize both of the edges here. But actually we can do it like this. So we consider 20 here, we consider 10 here. And after that, we consider 10 here, and we consider 10 here, and actually we consider 20 here. So we can clearly see that this is actually also a flow, because I mean, by these numbers, it definitely satisfies the capacity constraint. And also, I mean, looking at the 1, 2 here, it also satisfies the conservation constraint. Basically, the value, I mean, the in value and off value at vertices 1, 2 here, they're actually above 0. But actually, for this flow, actually the final flow value, I mean, looking at the S or T here, the flow value is actually 30. This is actually larger than you do the greedy strategy, and if you actually pick the path as to 1, 1 to 2, 2 to T here. So this is basically something we want to pay a specific attention to. And in general, I mean, there are instances that this greedy strategy does not directly work. Okay, so any question about this greedy algorithm and the reason why it is probably not optimal here? I mean, nevertheless, you can imagine that, I mean, this greedy strategy is probably not super bad. I mean, this flow value is 20 here. It's maybe basically, I mean, we have this flow value to be 20 and we cannot further increase the flow value here. It's probably not the overall strategy is totally wrong, but it's more like we are going into like an unfortunate case, whereas like a sub case, I mean, like a local optimal point that we don't really want. So basically, we need to like figure out what is the current situation. I mean, in general, I mean, we want to. I mean, we probably the point here is that not to totally, I mean, abandon this greedy algorithm. I mean, we totally build on something else, but maybe we want to make some fix of this algorithm, and hopefully we can have like a observation to fix this algorithm to actually make everything work. So let's talk about like a fix here. So the main, I mean, the main obstacle of this greedy algorithm is that basically, I mean, after having this flow value 20 here, so let's take a second look at this example. So it's basically you cannot like even further utilize this edge. I mean, it's basically that basically all this basically the edges of 2 to t, this is basically exhausted. You cannot further utilize that. And actually, basically this direction 1 to 2 here, you only have this direction 1 to 2, and you don't have the direction 2 to 1 here. But actually, for like a little bit a better strategy here is that actually maybe here, for instance, you look at this example. Even though I mean you only have like a 20 here to be the final capacity here. Maybe you don't want to your 20 here to all I mean go from this 20. I mean maybe here I mean specifically for this optimal solution here, you only utilize 10 here, and actually on the other hand, you use this edge as to 2 here, and there is another capacity of 10 here that you can utilize. I mean, here is basically what we want to make the observation here, that basically, I mean, we are basically running this greedy algorithm. It's probably not that bad. I mean, it's probably not bad. I mean, not that different compared to the really optimal solution. But maybe we want to have some kind of, I mean, of like going back, I mean, in general. I mean, in general, the point is that we really want to be a little bit flexible here. I mean, we don't want to like be greedy and we reach optimal and we don't make any adaptations here. Maybe here, I mean, if in some cases, I mean, if some edges, I mean, we will just run out of its corresponding capacity. This is not something we want. And maybe, for instance, maybe we can like, maybe we can actually, I mean, like decrease sum of FE to allow more, I mean, augmentations of ST paths. So this is a very important observation, especially based on this hard instance that we have been talking to. I think basically here, I mean, we don't really want to exhaust the 20 here. That basically actually decreases from 20 to 10 here and allows us to actually utilize this edge on S22 here. This is actually a much better idea that we can actually give, and actually then we can then give the optimal solution here. And we say that basically for this fix is that we really want to have some sort of way that we can actually going back here, and actually we are having this kind of a flexibility here, and I guess maybe hopefully we want to use this to give a better algorithm for the max flow. Okay, so this is probably still a little bit intuitive. So let me actually make this a little bit more formal here. So a formal definition that we are going to use here is that we are going to make a new definition that we call this as a residual graph. So a residual graph. So for the residual graph, of course, we need to first have like a flow network here. So assume that we are given a flow network, a G here, and actually, of course, a flow F here. So basically, we can then define the residual. We denote this as GF because the residual graph is actually mutually defined by both the graph G and also a flow F here. So actually defined, it actually depends on both of them. So actually the notation here we are going to use is that the residual graph we are going to denote as G of F of G with, we'll call this of G with respect to F as follows. So we have we make this kind of observation. So basically the node set of GF is the same as that of G. So the edge set is actually going to be a little bit different. I mean, compared to the original edge set. So here we say that for each edge, E equals to UV G, on which FE is actually smaller than CE here. So basically for such kind of edges, I mean, the FE is strictly smaller than CE here. This basically suggests that this is actually an edge that we can like put some further flow along that. So basically we want to include such kind of edges. So we include the edge EUV in GF with capacity. Basically, the capacity here we are going to add is basically the remaining value that you can further put along such kind of edge. So basically, we here put like a value of CE minus FE. And basically, according to this kind of intuition, it is very natural we call such an edge a forward edge. A forward edge. So I guess, let me also make an annotation here. So it's basically, the intuition is that here we want to consider, the leftover capacity on which we could flow forward. So basically, this is the definition of a forward edge. I guess this is a residual graph. Based on our discussion here, we probably not only want to consider the edges where we can, it's probably the current capacity is actually we have not read out of the current capacity, and then we can still consider making this forward, and we consider such kind of forward edge. But I think a very important thing here is that maybe we want to get something back. And also it makes a lot of sense. And maybe we want to consider, since we have forward edge, maybe we also want to consider some kind of a backward edge. And then again, I guess basically we can give like a similar definition in the other direction. So basically we say that for each edge, E equals to UV of G, on which, if we have the capability to maybe going back a little bit, to actually taking some back of the values, it definitely is probably going to be the case where the current weight is actually strictly larger than zero. If current FE already equals to zero, I guess there are just only a forward edge. You cannot take anything back. So there should not be any backward edge. But as long as FE is actually strictly larger than zero, we can basically include an edge. And actually, to make everything intuitive here, we want to consider like a backward edge. Basically, to do this, we just switch the direction here. So we consider like an edge E here. Originally this edge is U2V here, but actually for here, the definition of the backward edge, we are going to switch the direction here. The edge is actually defined from V to U now in GF. And then with the capacity, actually of CE minus, with a capacity of FE here. Because this is the value that you can actually take back of. And actually, basically we call such an edge a backward edge. So basically for this, it's basically a capacity. We can think back by pushing flow backward. So I guess this is basically the definition that we want for this residual graph. I guess maybe it is going to be more intuitive that we can show example along this. Maybe let me actually reopen this. So let's, for instance, just use this graph as example. So we have this. So basically, we have this graph that this flow that we got from the greedy strategy, and this is basically the flow that we got using the optimal strategy here. So let's draw the corresponding residual graph here. So here it is S, and here it is T here. And the vertex set is basically the same, so we still have T, and actually two vertices 1 and 2 here. So we need to pay a specific attention to the edges here. Basically, let's see, for instance, like this edge. For this edge, we actually ran out of the capacity here. So basically, the original capacity is 20, and the F value is actually also 20. So basically, for this edge, we are actually not going to have any forward edge, excuse me. We're actually not going to have any forward edge here because we have run out of capacity. But actually, the FE here is actually larger than 0, and actually much larger than 0 here. So there is definitely a backward edge here. So we can consider here like an edge. And the value here, as we just said, is just you put the value of FE here. So you just put the 20 here. So what about like, for instance, the edge from S to 2 here? So for the edge from S to 2 here, actually, this is only a forward edge because the FE is actually equals to 0. You don't even utilize that. You are flow here. So there, you don't have any space to make this, you take back this and make this like a backward edge. So here, you just have this to be a 10, according to this. But how about like the edge in the middle? On the edge 1 to 2 here. So the original capacity is 30. You only use 20 of them, and the 20 is actually it's larger than 0. So you use some part of that, but you didn't utilize all of those. So basically, for such kind of edges, you're going to have both a forward edge and actually also a backward edge. So here, you can clearly see that the value of the forward edge is actually going to be 10 here. Because the 10 here is the remaining capacity that you can further utilize. And actually the space that you can take back. Basically, since you already used 20 here, the backward edge is actually having another way to be 20 here. And then, I guess for the edges, from 1 to T here, it is going to be intuitive that you are going to still have like an edge with 10 here. And actually for the edge 2 to T here, basically you have actually run out of the capacity here of 20. You don't have any forward edge here, but you actually have a backward edge with capacity 20 here. So, let me actually mark this as the residual graphs. Oh, excuse me. Oh, as the residual. So let's also consider the other graph. So we have an S, and we have a T here, we have a 1 here, we have a 2 here. So basically, we can just also check. So basically here, from S to 1 here, we only have like a backward edge here because we have utilized the 20 capacity here. So we have like a 20 here, and we have like a 10 here. And basically, for the edge in the middle is that basically we actually have a further forward edge of 20 here because you have like a 20 space to further improve that. Actually, you have already utilized 10 here, so the value of the backward edge here is 10 here. And similarly for the other two edges, we actually got a 10 here, and actually we got a 20. Okay, so any questions about this definition of the residual graph and basically the residual graph on the specific examples that we are talking about? So here it looks a little bit weird. I actually draw this again. Okay, so any questions about the definition and examples? Okay. So I guess this definition of the residual graph is probably, going to be quite intuitive. At least from this example, we can clearly see that actually after considering this residual graph, we clearly see that our greedy strategy is not optimal. And actually along the residual graph, basically there is a further ST path. Basically, it's this path. So basically, there is a path along this. And basically, we also need to store the information whether a certain path is a forward edge or a backward edge. But nevertheless, basically, intuitively, we can clearly see that basically, as long as the residual graph, we actually have a path along this. So basically, this is a forward edge, So basically we have a 10 here, and actually this direction, this is actually where we get stuck, and actually we have another 10 here. This basically suggests that, I mean, after having considered this residual graph, and basically there is an ST path on this residual graph, it just suggests that we actually are going to further utilize this 10 here, actually decrease this value by 10 and actually increase this value by 10. And actually this actually gives us the optimal strategy here. So this is basically the intuition. I mean, only from this a quick look of the residual graph, you can probably see the intuition here why this is actually going to be helpful. I mean, basically, using the gradient strategy plus the residual graph, I mean, it is actually going to give you a good algorithm for solving the max flow. But nevertheless, I guess let's actually do this discussion. I mean, gradually, and let's finally see the correctness of this kind of ideas behind this. So I mean, the first notation, the first node that here we are going to mark here is that node if actually 0 is strictly smaller than FE, strictly smaller than CE. I guess maybe let me CE here. So then actually it returns in both a forward edge and a backward edge. I guess this is actually quite intuitive when we just discuss the relationship between the edge of 1 to 2 here. Okay, so I mean, based on our discussion just now that actually we look at the residual graph for this specific example. I mean, the idea here is that in general, I mean, for this residual graph, I mean, for this residual graph, it's basically suggesting the sum of the parts we can actually make changes to the flow. So suggest how we can changes to the flow. So specifically, so let P actually be a simple ST path in GF. So that is the case where actually a P does not visit on any node more than once. So in general, after we have defined such kind of a residual graph, then maybe we want to consider, I mean, ST paths along this. So in general, we want to consider like a simple ST path in GF. In general, the paths that don't visit any node more than once to basically facilitate our discussion here. For such kind of paths, we can have a very natural definition called a bottleneck. Bottleneck of P with respect to the flow F here. This is actually defined as the minimum residual capacity. So basically the residual capacity is just like the capacity on the residual graph. So basically the bottleneck PF is defined as the minimum residual capacity of any edge in P with respect to the flow F. I guess this is also a very natural definition that basically intuitively, I mean, the value we can increase. So basically here, I mean, we have a 10, we have a 20, we have a 10 here. But I mean, apparently the maximum value that you can increase is only the 10 here. And basically, I mean, when you look at the flow here, it's basically the amount that you can increase is exactly the bottleneck here. That basically the edge that is the minimum residual capacity. And basically this is the value that you can currently increase. And this is also a very important reason that we actually, why we want to specifically define this function, the bottleneck of a certain path with respect to the F here. Okay, so I think this is basically we get everything ready, and actually now we are going to introduce what is the algorithm that we can actually consider here. So the algorithm that we can actually consider here is called augment TF. So basically we write down this algorithm, and actually we are going to take a specific attention to the forward edge and backward edge, and we are actually going to get a clear understanding about their relationship. So in particular, let B equals to, I mean, if you look at the function here, I mean, I'm actually going to write down algorithm here. So basically, in the definition, we actually specified a certain path here. So basically, after we specify what is a path and what is a flow here, we can make the corresponding definition here. So we say that B to be a bottleneck of T and F. So basically, we can have such kind of definition here. So the next thing that we are going to do is that we need to take a close look at each edge on this path P here. So basically, we have like 4 each edge. U, V in P here. So if UV, so if UV is a forward edge, we just let E to be UV and actually increase Fe in G by B. And else, I mean, the else case is, of course, that the case where actually your UV is actually a backward edge. So in this case, we actually just let E equals to BU and decrease. Excuse me, decrease Fe in G by B. Okay, so this is basically the augment algorithm that we actually are going to consider here. So I guess this part, I mean, if UV is a forward edge, basically you just let E to be UV and just like further increase the Fe in G by B. I guess this is quite intuitive. I guess maybe let me explain a little bit about this part. I mean, the part where the UV here is a backward edge. I mean, considering the way that we define the backward edge here, I mean, basically in this definition, as long as we have a backward edge, so for instance, I mean, here, for instance, this is a backward edge. So as long as we have a backward edge, I mean, in the residual graph from U to V, it just means that in the original graph G, we have an edge from V to U, actually. And actually, due to the definition of residual graph, and actually this is the value we're going to take back. I mean, this is the reason why here, I mean, we actually write E equals to VU here, because actually the edge from V to U is actually an edge in the original graph G here. And basically, we are considering a backward edge and we want to decrease the corresponding values. And this is the reason why we want to actually decrease FEG by the value of B. And actually, let's do maybe, for instance, do a showcase here. So actually, for this residual graph, so basically, in this very specific example, it is not very hard to say that this is just like by writing the augment of the path. That actually I think, let me see. So we first have the P here. So the P here is actually just S2 1 T here, and actually the F is basically the F on the left hand side. And actually run this augment on S2 1 T here. We actually got the optimal solution that we actually want. So any question about this algorithm augment? Okay, so if there is no question, I guess, I mean, after proposing this augment algorithm, I guess we probably need to further make some justification for that. So let's then go to some results that we want to make arguments for. So basically a lemma that we want to show here. So the first lemma that we want to show is that the output F prime equals to augment TF is still a flow in G. So I guess this is a relatively easy to understand, but nevertheless, let's give a complete proof here. So since F prime differs F only on edges of P, we only need to do two things. So basically, we need to check the capacity conditions, because basically the restrictions on a flow is basically the capacity restriction and the conservation restriction. So basically, we need to check the capacity conditions on these edges. And check conservation condition at each internal node. So I guess for one, I guess let's just check this two conditions one by one. So basically, for the first thing, we need to check the capacity condition on these edges. So for one, I'll let UV be an edge of P. So actually, if E equals to UV is a forward edge, so we need to make a we need to make a differentiation between different cases. Want to discuss about the cases where it is forward edge, and then discuss about the case where it is a backward edge. So for the forward edge case, I mean, then it's residual capacity. It's basically a CE minus FE. Thus, we have basically still we have a zero smaller than FE here. Is actually going to be, I mean, we just write to be F prime E here to be the F in the, I mean, we say F after augment. So the F prime E here is going to equal to FE plus the bottleneck PF. But according to the definition of bottleneck, we know, and actually we are considering a forward edge. This is actually going to be smaller than FE plus actually a CE minus FE. And actually this equals to CE here. So this is the case because we are actually considering a forward edge, and we know that actually the bottleneck is this value, and actually this value should be at least larger than or equal to the bottleneck, because this is the remain capacity that you can like further increase along this, and actually this is the value on the residual graph here. So it is basically clearly seeing that using this chain of inequalities, we can clearly see that actually for a forward edge, I mean, doing such kind of, I mean, you just do this augment. They're still going to keep the weight of the, the function value of this corresponding edge is still going to be between 0 and the value of CE here. So actually, some of the places, I guess I'm writing like this. Yeah, I guess I just like to make the notations clear. So on the other hand, if UV is our backward edge, arising from edge. I mean, if it's a backward edge, in the original graph, it should be an edge VU belongs to the edge at E here. So then is a residual capacity. Is FE. So actually we have a CE actually larger than FE. Is actually larger than F prime E, because actually the F prime E is actually something like FE minus the bottleneck PF. The bottleneck is always something non-negative, so we have this inequality here. But nevertheless, we know the bottleneck is actually the smallest among all the ways that we can put here. But actually, for the backward edge, I mean, as long as we have this kind of definition here, because the residual weight is actually on this edge, at least as large as the bottleneck here. So we know that this place, actually the bottleneck here should be smaller than the value of the FE here. And actually we know that this just equals to 0. So we're going to have another chain of inequalities here to promise the correctness of our algorithm. So basically for 2, I mean, in general, the conservation constraint is actually still going to be satisfied. I guess because we are talking about like the ST path P here, it suffices that we need to consider V be an internal node. So let me actually quickly finish this because the argument is actually quite straightforward. So basically, the amount of changes entering and exiting be cancelled associate each other. F prime still satisfies observation. And it finishes the proof. I guess basically for the second point, it should be relatively straightforward. I mean, the conservation condition, I mean, at the vertices in the middle, I guess we consider like this kind of augment, and basically we put the same value in, basically always at the same time. Actually, the amount of entering and exiting is definitely going to cancel each other. So we still have this conservation condition here. Okay, so this basically finishes the proof of the lemma. Let's take a break for 10 minutes.